that going on over here. Hey, Kruifa, welcome to the stream. And there we go, my tweet is out. And here we go. So I've kind of been in the middle of programming all day, and I just wanted to wait for Handmade Hero to wrap up, which I just did. Alright, so before we get started with the actual stream proper, oh, is the audio an issue? Is the audio an issue? Alright, Jim says the audio is okay. I'll let you work on that over there, Dave. So you can't see the little purple dot, Jim, on Discord? Because I do. I see a purple dot and it says streaming 4coder bonus day under my name. Anyway, so let me give everyone the rundown of what I've been working on since yesterday. I got the rest of the built-in UI that I'm going to replace is replaced. So basically, the ability to switch themes, like this stuff right here, is all in there. I've deprecated this thing. I don't really like supporting it. It's a pain in the butt, and honestly, just it's a distraction from getting real things done. Same thing with this font stuff. It's all neat to be able to have there, and it kind of proves that the font system works when I'm building out the font system. But actually supporting it is a big pain, and I just don't like it. It's distracting. So the only thing I replaced was this list here, and worked out some bugs, some remaining bugs with the other stuff. And now I've switched gears since yesterday. I finished the that stuff, and I got to work on some other things that I haven't really talked about on stream yet that I wanted to work on. And we're not going to have a full day of me streaming, like 6 to 8 hours. I'll probably just do 2 or 3 hours today to make up for my missed day yesterday. But I do want to give you an update of kind of what we're working on so that you know what I'm talking about here. So let me first introduce you to the important new type that's been introduced, this dynamic scope right here. So the dynamic scope is basically an abstraction of something I built a few weeks back that lets you. The thing I built a few weeks back was the ability to set dynamic variables on a view. So you could say this view has these variables attached and set those values, and then you wouldn't have to manually inside your custom code keep track of tables of views and map IDs to map view IDs to the states that you were storing. I wanted to get to the point where you could just say, here is the dynamic, like here's the view ID, and here's the variable I want to query or set, and have it just handle that for you inside the core. So we built that a few weeks back, and I started going in to do the same thing for buffers, so that buffers could also have these variables attached. And my immediate feeling on it was that I didn't like how duplicated the API became. Let me show you kind of what was happening. So let me go to variable set. So basically there was like this variable set and variable get, and there was one for view set variable, view get variable. There's also a view create variable, and then the buffer had the same three things again. And I just didn't like the fact that there's like this whole thing that was basically an interface to the same system. A dynamic variable thing existed in the view and in the buffer. It was the same stuff, and I just wanted to get to the point where I could push in or pass in a dynamic scope thing right here, which I'm still kind of in the process of transitioning this API over from a different naming scheme. But I wanted to get to the point where you could pass in a scope, and that scope could come from different places. So that scope could come from a view, or it could come from a buffer. And there's two basic reasons why I wanted this. One, get and set weren't the only types of operations I want to do on scopes. I want to kind of expand out what you can do with this scope. And views and buffers aren't the only kinds of places where I wanted to get scopes from. So when I had, like, you know, 3 calls, get, set, and create variable type, like in the layout, and then 2 different types of scopes that might go with, that was like 6 calls. But if I added a third one, like a global, that you know, increase the dimensions of this rectangle of different crossings of the type of scope that I'm dealing with and the calls that go to a scope. Because if I want to add allocate memory, like allocate raw memory onto one of the, as a call you can do as well, then what would I do? Like, I would end up with 3 times 4, so now I'm up to 12 where I started with 6 just by adding in a few features. It's not great. So I wanted to get down to using these dynamic scopes as sort of an abstraction between what the object is that the thing is attached to and what your operations are doing on it. So now what you do is you set and get variables on this dynamic scope, and we're going to build out some other things you can attach to dynamic scopes and stuff like that, operations that work on dynamic scopes. And then you can get dynamic scopes using different methods. There's buffer get dynamic scope. So that gets the buffer's dynamic scope, so that instead of calling buffer set variable, you call buffer get dynamic scope and then set variable, like dynamic scope set variable, basically, right? Same thing with view. View now has view get dynamic scope. I've also added a global dynamic scope, and that's just this one very simple call that returns the dynamic scope struct that is set up to reference the global scope. And let's see. So that's the main thing. But the other big feature I was trying to get out of this, that I'm still in the middle of doing the rest of the implementation for, is an intersected dynamic scope. So the idea of an intersected dynamic scope is you can take 2 of these objects with variable lifetimes, like a view and a buffer, right? Views can be created and destroyed, buffers can be created and destroyed, and the code that creates and destroys these can live anywhere in the custom layer. In fact, 2 different authors of custom code might both write plugins that both create and destroy certain buffers or certain views or both, right? And there might be a third plugin that doesn't know about how those 2 guys are creating and destroying things, and they're trying to attach information onto a buffer. And the dynamic scope system as it is allows you to do that. But what if you wanted to attach information onto a buffer and a view at the same time, so that it's information that says something about the relationship between that view and the buffer, like where the cursor and view scrolling position are when that view looks at that buffer. To make these types of things composable, it's helpful for the core to manage that. And just like with having the core manage the lifetimes of things that get attached to individual objects, it's helpful to say that there is also a lifetime scope for something that is attached to both this view and this buffer, so that if either one of them closes, that's the end of the lifetime of this piece of data, right? This data only makes sense to exist as long as both of the objects to which it is an intersection the two objects that intersected to create this data still need to exist for this data to mean something. So actually building that out is a little bit of an interesting problem that I've been dealing with since yesterday. And I got some great help from other people. I can't take credit for coming up with all the ideas, both for the API design and for the implementation details. And I've just discovered some bad news, which is that this doesn't have virtual whitespace enabled. So I'm going to have to deal with the fact that this file has gotten too big for virtual whitespace to run right now, and I need to deal with that on another occasion because it's kind of complicated. I can't just split this file up. Okay, so there's the catch-up. Now let's look at how everything works so far. When you get that intersected dynamic scope, what it does is it builds an array of these lifetime object pointers. And so there's a lifetime object, one lifetime object for every buffer, one lifetime object for every view. If you passed in a dynamic scope here, should be like intersected scopes and count, I guess. Then for each of those intersected scopes, if you got a buffer or a view, you just put that into the list of object pointers. If you got a scope that was already an intersection, then we get out the array of objects that were a part of that intersection and we put them in. There's no such thing as you make a new dynamic scope and it's the combination of three intersections, or an intersection of three objects, and then you use that as the intersection of one of those three objects again to get another one. If you take objects A, B, and C, and you say, give me the intersection scope for these three objects, and then you take that dynamic scope and you say, give me the intersection scope for this thing and object A again, you get the same thing back. You only get a new thing if the set of objects changes. Also, the global scope doesn't contribute to intersections because the global scope always exists, so it doesn't affect the lifetime of anything to say that you're intersecting it with the global scope, because it's kind of like saying you're adding 0 to a number. The thing that comes out is the same thing that you put in when you intersect with global. So it doesn't emit anything into that array. Then, once we have that array, we process it to make sure that it is sorted and deduped, so that there aren't more than one instance of each object in there. We sort it partially to make deduping easier, but also because we need to be able to do comparisons between sets. And an easy way to do set comparisons is to sort your sets and then do a memory compare afterwards. Set comparison isn't just a memory compare always, because in a set you don't care about the order of your objects. So we have to find some way to make it work even when the inputs come in different orders. If they're the same set of objects, they should compare to true. So that's what that's the other purpose of the sort serves, is to allow us to do memory compares for set compares later. Then what happens is I take that array, which has now been generated from the input handles, or the input scopes, and then trimmed down and like pre-processed to act as the smallest possible definition for a set that we can easily compare to other equally pre-processed chunks of object pointers. And then we send it to the implementation of the dynamic variable system, which I have not yet implemented, which is lifetime get or create intersection key. Right? So what that does is actually generate the key object, a key object being the thing we are going to use to look up the dynamic variable blocks later. It's also a key in the sense that when we pass it in here, we've now sent in a bunch of objects, and we are looking to see if this lifetime key already exists, we'll return the same thing. And if not, we are creating a new key, right? The key basically being a wrapper around an array of object pointers is a way to look at it. That couples it with its dynamic variable block. Okay, so how does this implementation need to look? Well, The first step is going to be we need a way to iterate all of the existing keys, which we don't have right now, and find the key. So a couple of options. One thing to consider is I don't really want to end up in a situation where I have 1,000 keys and I have to compare every new key that someone passes in with all 1,000 of those, because a key comparison will be a little bit expensive. It could be 8 or it could be like 16 or 24 or 32 bytes of comparison per each key that I check. And there could be like 1,000 keys, and that could happen maybe 10 times per event. It's just a lot of waste that doesn't need to be there. So one way or the other, I'm probably going to want to hash the set. I want to do some kind of set hash operation to turn it from a variable width thing to a fixed width thing that I can compare that's like 64 bits. And only when that comparison passes do the deep compare to make sure that it's the same set. And then the other thing I want to do is probably, once I've already bothered to put in the hash, also do a hash table, because that will let me skip the iterating the 1,000 keys, which is really the part that is the most expensive anyway. So we're going basically for a hash table where our hash keys are sets of objects that have been pre-sorted so that we can do set operations on them pretty easily. So I'm going to add to this a hash value, and we're going to want to figure out how to compute that, and then we're going to want to have the ability to put that into the table. I say let's just go straight whole hog and go for the whole thing at once. So the key table is going to just be a bunch of lifetime keys, I think. We can't just make it an array of lifetime keys because the pointer values of these things matters. So it's going to be a lifetime key pointer array, and that means in order to look something up, you hash it, you go to its pointer in the array, and that indirects you to the key. But that's going to make it hard to do the hash compare. So what we're really going to do is we're not going to store the hashes here. Yeah, we'll store the hashes here. Right. So the fast compare is look at the hash in this part of the table and see if it matches the hash we have. If it does, then we go through the indirected pointer at the same index and we do the deep compare, and if those match, then this is the key we wanted. This way we only ever go through that extra level of indirection when we already know that we have a hash match, which should cut down on the waste that happens because of this extra indirection, basically down to 0, or down to like 1 time per lookup, right? And then we're going to want to know the max size of the table so that we know what modulo to apply, what modulo value to apply when we're sticking things into the table. And I usually like to keep track of the count so that I know how full a table is getting, so that I can resize it before it gets too full. Because if you allow it to get like 99% full, your hash table kind of starts to become just a linear array anyway. And then we can take the lifetime key table, plop it down right there, and there we go. Now, doing that complicates more than just how we create this, because now I have to create that lifetime key table and do all the stuff that is involved in the maintenance of the lifetime key table data structure, right? So there's a right now I guess that the allocator doesn't get initialized ever, which is actually fine. Yeah, when we allocate an object off of it for the first time, that's when we actually grow that thing there. We haven't implemented the thing that grows the key memory or the table memory yet, so that's all going to actually happen as a consequence of implementing this. Okay. So, get or create intersection key. First step, we need a hash of our set. So here's our hasher right here. lifetime get or create intersection key hash. And that's just going to take in the object that needs to get hashed, which is this array of pointers, and then we're going to hash it. And now what I want to do is, I don't want to do anything too fancy, I guess, but it is a little important in my head to get this. At least I believe in my head that it's a little bit important to get this to be a good hash. So we're going to do a quick off-screen research project. What shall I Google? Hash array of integers. Hash function for an array of integers. How does this look? Do 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 do. Any other good suggestions? As that didn't seem like one. Nope, also not helpful. Do 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 do. Oh my goodness. Over the past, I've built a general hash function for the hash table lookup. Most of the two. I'm not really interested in your hash table. That's not even the right type either. Okay, guess it doesn't come up on the first page of Google. So, I'm just going to make it up. We're going to start by getting this as an integer. I want to drop the first 3 bits. And I only really care about let's see, how many of the bits do I care about after that? 32 minus 3 is 29, about 20... Okay, 29, about 2 or 3 of the top bits don't matter either. So I feel like the right thing to do... Well, maybe I just leave those in there in case they do show up. What I'd rather have is something like this, actually. So, well, let me think this through. If there's a 1 in the bottom bit, then... No, that wouldn't work because that's... Okay, I actually want to do this. Okay. Alright, so that'll either give me a 1 or a 0. It'll probably give me a 0. Oh, if it ever gives me a 1, then I shift up 1 and therefore put a 0 where it leaves behind that result, which I guess means once all that's done, I want to do this. Alright. The bottom 2 bits will always be identical now. That's lame. Hold on. I'll think of something smarter. Let's do this. Alright, that'll do it. So, it has the following features. It starts as a non-zero, so if all of the x's were somehow 0, it would still change because we're hashing this against this, and so the length itself plays a role. And then I grab these x's and I remove the bottom 3 bits because these are coming from pointers which will all be 8-bit aligned. And then I randomly, and by randomly I mean based on what value I see in x, decide how much more to move that x around. I'm happy with that. That's not, brilliant, but it has all the basic properties that look natural, if not like proved out mathematically to actually mean something. At least I'm covering the bits, I guess is what I'm thinking. The only thing I'm not doing very well is making sure, I guess after one pointer, we don't have any guarantee that, so what I should actually do is bit shift this by way more. Even more than that. Okay. I'm gonna go with that. I think. Guess I should do this though, because if I keep XORing that like that and I get a stream of zeros, I would just be flipping a couple of bits back and forth forever. Yeah, so I'm going to do that. Cool, okay, I'm cool with that. So there's how we get our hash. Don't use this algorithm at home. Use at your own risk. The software is written as is and is not necessarily provided to you in any way, although it would be except in the sense that you can read it and write it for yourself. In that sense, it is provided to you as is, with no guarantee of warranty, etc. Read someone else who wrote it correctly. You know what I mean. Alright, so that's the hash. What's the next step of this algorithm? We want to look up in the hash table to see if this key already exists. So I just need to provide the key table of interest. I need to provide the hash that I've just computed, and I need to provide the object putter. There we go. So that's going to look like this. Key table lookup. Key table hash, and then the object pointers array and the count. That should just say count now. That's too wordy. Doesn't need to say member count. Doesn't mean that exactly anymore. Okay. So now we want to look up in here to see if this key already is stored somewhere in this table. So the way that'll work is we want to, why don't we turn these into U32s? We're going to get first index equals, we take the hash modulo the table's max. Now before we do any of this, we need to make sure that the table's max is greater than 0 and the table's count is greater than 0. If none of that is true, then we'll just do that. As an empty table does not contain anything, that is the correct behavior and prevents us from moduloing by 0. Then we are going to copy that and begin the loop like so. After each step of the loop, we will take the index and plus equals 1. If the index becomes equal to the max, so we're going to take the max value out of the table right off the bat, and then if that happens, then that'll go to 0. If the index ever becomes equal to the first index, then we can break. And so now, the last thing to do is to look up the hash in the hashes and see if we found what we were looking for. So that's in the table's hashes. If hashes index equals the hash we care about, then we have more checking to do. So if these are a match, we want to look at the keys in the table, and that'll give us a lifetime key. And then what we can do is say if there is a positive mem comparison between the object putter array and the key's own members array, we'll store a mem compare size or set size thing there. So I guess before we do that, we can also just verify that the key's own count matches our count. Then we do the mem compare, make sure that those are equal, and that means that we can plop up here a umem set size as count times the size of one lifetime object pointer. So if the key object that we pull out from the table matches the has a object pointer set that matches the object pointer set we have, then we have found the key we wanted. We can just return it. Done. And so that means we don't actually want result sitting around being a jerk. We'll have it do that. Alright, there we go. So that's not bad, but what I do need to do is I need to set up some special hash values. So this hash must be guaranteed to never return either of these values. And those values are going to be lifetime key hash empty equals 0, lifetime key hash deleted equals U64 max U64. There we go. And so after all this, if hash equals this, then hash equals 1. Hold on, let me think. There's a different way to do this. If I always override the top bit there, I could do this. Alright, so my hash function always returns a 64-bit number with the highest bit set, which means that my specials can just be values. So I basically have 63 real bits of hash, because the 64th bit at index 63 is always set to 1 in my hash values, which I am fine with. And then, oh, I guess that means that this should be like that. And then that way an empty hashes to that particular thing, you know, an empty array, which would never come through here anyway if everything works correctly, but it, you know, is handled. And so any specials I ever want just have to make sure to not set that bit. So like 0, and then instead of this what I can do is say and not bit 63, right? And as long as all of those have and not bit 63, we're good. As long as all of those have or bit 63, we're good. Although, why would I do it this way when I could just do it this way? Yeah. Okay. Alright, moving on. So while we're going along, if the hash we look at this index matches the thing we're trying to look up, then it exists, then it probably exists. We check the key directly and make sure we fully match, and if we do, we return that pointer. Else, if the thing we look at is equal to empty, then we're done, because whenever you find an empty slot, it means that nowhere between the hash and now did you find the thing you were looking for, which means the thing you're looking for isn't here at all. If we see a deleted slot, then the thing we're looking for could still be there, because the thing we're looking for might have been inserted before that slot was deleted, and so it could be later. So we have to keep going when we're doing a lookup. Okay. So we do that. If the existing key does not equal 0, then we just return that right away, and we're done. So the user passed in the set of objects, we looked up in our table and saw we already had such a key, and so we returned it to them. Now things are going to get crazier, because the next thing we're going to want to be able to do is add a key to the table, and that's just going to involve a whole bunch of stages. So let's first allocate the new key. And to do this, we're going to look at how we allocate an object, because it's going to be kind of similar. So the first thing we want to do is go to our lifetime allocator and pull out a free key from the free list. If the new key is 0, that means there's no free key node sitting on the free list right now. So I say we're going to get this many new keys. So we grab that memory for the new keys, and then we're going to iterate those new keys. And that looks like this. There we go. So we iterate the new keys, and for each of them we're going to push it back onto the free keys list. There we go. So the new keys get pushed all onto this list. And then we increment the counter on the free keys. And we set our key pointer like so. Okay. So now we have a new key. Good. Next up, we need to stick that into the table. So before we stick it into the table, let's fill out all of its members. How about that? So the new key needs to get removed from the current list, the free list that it's on. And then we want to well, this gets interesting. We need to figure out where the memory is going to come from for this array right here. And then we need to initialize that. Okay. So that's not really a mystery. The new keys count will be this count right here. The new keys members will be pulled off of this, so a pointer to a lifetime object, general memory, and then the size of a lifetime object pointer times the count. Then we'll mem copy into the new members from the object putter array. And so just like that, we've created a new key that has its members pointed to the new array of members that it's allocated. We've filled that with the correct memory and set the count so that it can compare against others in the future, and so that it can iterate its members whenever it needs to. And then we want to initialize the dynamic variables. And that just looks like this. Dynamic variables block init. Which just takes the general memory pointer and the dynamic variables. Okay, so this creates a key that it pulled off of this arena, or off of this free list. So it pulled a key off a free list, initializes the key, and now it's ready to stick it into the hash table. Okay. So to stick it into the hash table, we'll make a call to lifetime key table insert. Lifetime key table. Wait, no, I just need whatever I passed up here. There's the hash, and then the new key that we're inserting. Yep, new key. And then finally we can return the new key. Okay, so now we just need to write the code that describes how we insert into that table. The first two members I can lift from over here, and the last member is a lifetime key pointer like that, and this is going to look quite a bit like the code above it. So the only thing it might do differently is this might also want to get the general memory, as this is going to be responsible for growing the table if it needs to. So let's take a look at the max and the count, which, by the way, if we, we're fine there. It's down here we have to do something. So if max equals 0, or if the count, and a good ratio that I generally like is like 5 to 6, so if the count times 6 is surpassed the max times 5, then what we'll do is say new max equals clamp bottom. You got to give me at least 32 slots, maybe even 64. Actually, maybe even 256. You have to give me at least 256 slots. You know, why don't I take 256? Yeah, that's not a bad idea. Calculator, 256 times 6 divided by 5. So we'll do like 307. You gotta give me at least 307, and then double the previous max. And now we have to do a table move, which is always a lot of fun. Yeah, let's do this. New table dot count is going to start off at 0, so that one I don't change it. So the new table dot hashes is going to get, well, let's do that all in one batch, shall we? So first things first, the new table's memputter is going to come from general memory allocate on the general memory arena item size times the max, and the item size is the size of two different things added together, the size of the new table's hashes. Come on. Stop hitting wrong keys here, Alan. There we go. And the size of the keys, right? So we get the new memory there, and then we want to assign this part to here, and then we'll take that plus the new table max and put lifetime key pointer there. So now we have the memory. Now what we have to do is iterate all of the existing keys in the old table and move them to the new table. Okay. So we have some options to consider. One thing we can do is just iterate all of the slots that exist, and the thing is, if we iterate all the slots that exist, we're going to be doing about 6/5 too much work because we never allow the table to be completely full, which means at best we're getting 6/5 too much work. We could be in a situation where we allocated, well, I don't know. The first time we ever allocate, I guess this only ever happens when it's no worse than 6/5 of the full linear thing. So it's just a linear scale factor of the amount of work we would have had to do anyway, and all the only extra work we'll be doing is checking some hashes that don't have bit 63 set and skipping them. Okay, so that's actually not that bad. And okay, so I'm going to just preemptively do something because I know I'm going to end up wanting this. Lifetime key table move general memory lifetime key table table return the new table, copy. And right here we're going to put new max. And so now this is just going to be lifetime key table new table equals lifetime key table copy general table new max. Okay, now the reason I'm going to want to do that is because there's going to be another circumstance that we're going to end up running into maybe today, maybe later in the future for optimization purposes, where the table hasn't grown for a long time, but it's inserted and deleted so many times, it's in so many deletions from the table that it is filled with deleted slots, which means that when you don't have a match, you have to do a full iteration anyway. So basically, once in a while, if the number of dirty slots gets too full, you want to move to a new table anyway, even though it's not running out of space for storage. It is just losing efficiency for searches, and so to avoid, constantly paying a linear time thing that does the search that you don't need to do, we'll have a thing that looks and goes, okay, to avoid those, we're going to do a move to a table that's only a little bit bigger, and that way all the slots will be empty again. There's some smarter stuff that you could do so that deletions, like if I wasn't doing linear searching, for instance, linear probing, if instead I was doing chaining, then this wouldn't be a problem. And there's some argument to be made that I should be doing chaining, Because if I was doing chaining, I could also make them move faster in other ways. Because once I'm already doing chaining, there'd be no reason I couldn't chain all of them together, actually. And we would just use... That's actually really interesting. I would have my hash table would be pointers into the chain, and whenever you insert or delete something, you're removing it from the chain, not doing anything to it in the table unless you've deleted the last member of the chain. And you can discover when you're at the end of your subchain by looking at the hashes of the things you're visiting and seeing how they look modulo the table. And then a table move would just be an iteration over all the elements that are chained together. That's fairly intricate, and I've never implemented something like that, so I don't want to do it today. I want to try that when I'm just practicing first, because this is me implementing something that I want to ship sooner rather than later, and that's more like something I'd like to practice, you know, playing around with before I try to ship it. See if I can get the sun out of my face a little bit. Okay. Anyways, continuing with this for now. So now we have to do the move. So if we visit all the hashes and any of them do not have, or do have bit 63 set, so if we do a mask against bit 63 and don't get 0, that means that we want to move that to the new table. Which means we want to call insert, basically. And you know, eventually all of these are going to want to move higher up for reasons like that many of them are going to want to move up to there. So let's start from there, and while we're doing this copy, what happens is this gets declared right there so that insert can call it. And then lifetime key table insert gets called again. This time we'll pass it as 0, and we'll say that we assert that general does not equal 0. So if we end up with a case where it does equal 0, it's because we went down this path when we weren't allowed to go down that path. We're adding it into the new table. What are we adding? We are adding the key and the hash. Yeah, the key and the hash stored at slot I. So we insert each of those into the new table. We don't pass down a general memory to that insert so that it's not allowed to do a grow operation, and will fail if it has to do a grow operation. But it shouldn't need to do a grow operation because we've done the work here to make sure of it. The order doesn't matter, except that it means something in my head about what we're expressing, so that I can read it more easily, that we never allow it to go below that, and then even if this was a 0, we don't allow it to go below that because this is the minimum size of a non-zero table, whereas this is just figuring out, making sure that this is big enough to contain this. And so this applies universally, whereas this applies in the more local case. So in my head, this is the right order. But it really makes no difference. In fact, the more proper thing to do would be to not nest them, because the macro expansion for that is a little bit not good. So there we go. So now we have the new table. We're then going to general memory free the existing table from its memputter member, just like that, and then the table we have can just become the new table. So all the pointers in the new table get moved into that table there, and we just throw away the temporary stack storage for the new table struct, as it has now been stored in the thing that we call the table. Okay. Now we want to insert a key. So we are asserting that there's enough space, and now begins something. So we'll do that, and then something more like this. Okay, so we grab the table max again. We do it again because it could be different now. Compare that to the count, get the first index, get the hashes pulled out, and get the set size of the thing. Okay, so that's different. That needs to come from the key count now. Okay, and then we're going to start iterating through. I guess we're also saying that we shouldn't actually find any matches, so I'm gonna just not even bother with this. Basically, we're going along, and if we find an empty slot, or if we find a deleted slot, then that reminds me about something. When we do the table copy, before anything else happens, we should memset this to 0, so that all of its slots are initially empty. And then if the slot we're looking at has the space to store somebody, then we do this. And there we go. Okay. So, hashes index. Right. So we just need to set the hashes equal to the hash for this object, and then we set the table keys to the new key, and then the iteration can do everything else the way it does in the other case, right? We find either of those, we're done, and we stored it successfully. We are assuming we will always store it successfully because we're literally growing it manually, so it should fail up here before it gets here if it's going to fail, and this shouldn't be allowed to fail either if we do our jobs correctly. And if nothing crazy happens, in terms of what the users try to make this system do. Let's see. I think that's everything. Besides the cleaning the table when it gets dirty part. Ooh, do I not have all that defined in this code base? Bit. Oh, I do not. That's annoying. So, let me change some stuff. I'm going to replace this with this. I'm going to replace this with this. I want to replace this with this. And I want to change this to this. And then I want to... Do I have one time set up on this project? No. Oh well. That's not a problem. I'll just do it manually because, hey, it's not going to kill me. Boom. U32 to U64. Replace all occurrences of 1 with U60 parenthesis U64 1. Okay. My bad. I didn't specify myself clearly enough. Please convert all instances of parenthesis 1 to parenthesis 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 U64 1 parenthesis. And then we're going to add 32 to all of these. What's the easiest way to do that? So replace every occurrence of this with this with this, this with this, and then this with this. Whoops, and this with this. Whoops, and this with this. There we go. Okay. Then the last thing to do is to rename all these. Okay. Okay, so now, okay, if you're going to be complaining about that, then how about this? Alright, now we're getting to some real problems. Right, I don't really use umem in this codebase because it's not set up for it. Bubbles, yeah, I got your video. Sorry I haven't responded yet. It's been, it's been a busy week. I intend to do a bug fixing pass on this build, and so your bug has been sorted under bugs for now, and I'll take a look at it when I'm doing a bug pass. Although I'll probably I haven't looked at it yet, but I'll probably take a look at it before the end of the weekend just to make sure it's not something that, it might be something that you can fix without me having to do something, and I'll find that out tomorrow when I take a look briefly to make sure it's not that kind of thing. Sorry I didn't respond. It's been a busy weekend. So these are counts. Lifetime key table insert needs the general memory allocator in case it has to grow the table. Okay, so man, that sun is still finding ways to get at me. So that builds makes me kind of nervous because I feel like I must be forgetting something still. This is such a big system. So get or create new intersection key. We first see if the key already exists, and if so, we return that one. Then we allocate a new one, possibly extending the free list in the process. Technically, this is a part of the allocation process. Then we initialize the new key. That's something I forgot. So we have initialization for the key. I'm not convinced that the deinitialization for the key is fully finished yet. So when we free a key, we remove it from all of its objects. Good. But then yeah, it's only getting called right there in a loop. So I think after it's been removed from all of its objects, the other thing it needs to do is deinitialize all of its own information. So it needs general memory free. I'm actually going to be happy with myself if I pull this out separately. Deinitialize key. Let me think something through. I was saying to myself earlier I might want to mark a key as, yeah, and not do that until there. in the future, right? I don't know if I need to do that right now, but that would mean deinitialize immediately all of the keys. Deinitializing would involve removing from the tables, deleting them, or freeing all the memory for the block and for the object set, and then putting oneself back on the So there's deinitializing the key, which does everything besides putting it back on the free list. And the reason we don't do that is because we would want to wait until that's done. I guess this deinitialize also wouldn't be allowed to remove... Okay, I see. Deinitialize first, and then later we have to free stuff. And the thing we free is the key's members off of the general memory. And we also want to do a table erase. So remove myself from the key table, and then finally free the key, putting it back, or free the key's pointer there, and then finally we're going to put the key back onto the free list, like so. So that does the actual freeing work. Along with this removes it from everybody's radar. The deinitialize part will be the part that is responsible for this. As well as anything else that needs to happen when that... Right, okay. So that's the deinitialize. It's just the call of that. So I don't actually need a separate procedure for that. That can just happen there. And the rest of this is the free, which is fairly complicated because it has to take itself off of all of the lists for all of the objects, and it has to take itself off of the table for the keys, lookup table for the keys, and it has to then free the memory that it stores for storing its own key value, and then finally put itself on the free list. So that's all freeing, and then deinitializing is just the process of removing its dynamic variable block. Oh, so Valibus asks, once you've customized how a language set of keywords works, how do you set that a particular file gets highlighted, like get by extension? So one thing to look at is in your default hooks, there's a list of which files get treated as code and how an extension pairs up to a particular language. So like you can see, here's where all the C++ extensions get paired up to the C++ language context. So if you haven't done this part yet, you still have to do that. So like for instance, this has GLSL treat as CPP. If you want to get it to treat it as your GLSL code, then you need to make your own version of this hook that right here does that, and that'll probably be a little bit of a pain because right now this isn't set up to be super easy to work with, so that every time I ship a new build, you'll probably have to make the same edit to this line of code and this line of code to bind to your GLSL, or you can make a copy of this and edit it from and have it keep it in a different file. But this is quite a big function that's liable to change once in a while. So even if you have your own copy separated, when I do change it, you might miss out on that change and be the worse for it. So it's up to you how you deal with the fact that this isn't quite done yet. But in the meantime, what you can do is probably the easiest thing is to just edit this every time and say GLSL here and here, and include your GLSL language data up here. And you can also add new stuff there. Now, just because you have it in this list doesn't necessarily mean that it's going to work. The other thing you have to do is make sure that that it's in this list. If it's not in this list, then even though its language context gets set, it won't be treated as code anyway. So you can control from the config which files are treated as code, but then to control their language context, you have to go to the default hooks here and change this code. Yeah. Yeah. Now, yeah. Yeah, so what happens is first it gets the code extensions from the config file, then it makes sure that the extension is in there, and once it knows that the extension it's looking at is one of the code extensions, then it uses this to decide on the context. That's the whole picture. Okay. So, oops, sorry. Lifetime key hash. So the other thing that I still haven't done is when I create a key, I put all the object pointers into it that it points to, but I don't do the opposite, which is take all of the the key pointer and put it onto the object, the set of objects that have just got a new key. Right? So basically what I'm saying is when you're doing this free part, this part here that looks really complicated is so complicated because, well, that's kind of a part of the dinit, but it's like free, remove from objects, and then free. It's really a separate kind of operation. Volbus asks what I'm working on today. I'm working on a sort of, I guess you could call it a memory management API for the custom layer that allows you to tie things to the lifetimes of buffers and views in fairly intricate ways so that you can allocate things that will be around for as long as they are necessary in a very natural way. So basically the idea is you can use any buffer or view or set of buffers and views as a key to get back a scope which you can then set dynamic variables into, and you can allocate things into that scope so that when that scope dies, like for instance if a view closes, its scope and all of the scopes that were created with it as a member of the key set all get closed. This is useful because if you basically are using like a view and a buffer as a pair as your key to get to a particular scope, then as long as those two things are still the same pair of like that those two objects still exist, then the memory you set, the data you set for them, you will expect it to continue to exist that way. As soon as either of them dies, that object that is the pair of them also no longer exists. And so at that time, the things you set in there get freed too, and you don't miss them because there's no way to query for them anymore, because the tuple that you used to initially query for it and set it is now impossible to form because of the fact that one of the objects in it is gone. And this is going to be very useful for features that involve cross-buffer or view-buffer coupling type things. Oh, there's already a couple of things like that in 4coder. Some of them that are obvious, like the fact that there's a jump buffer with lines that you walk through, and then those jump you into other lines of other buffers, and the markers that get placed in those buffers, their existence is is contingent on both of those buffers still existing. There's other ones that are less obvious because they never worked, such as internal to 4coder, there's a thing that tries to keep memory per view about where in a particular buffer that view likes to look, but it's very broken, and so I basically kind of deprecated it, but some of the code is still sitting there. Once this is fully in place, one thing I'll be able to do is pull that out of the core completely and implement a much more stable version of the same thing on the custom side. Okay, so, and we're basically just working on this fairly intricate data structure that enables that intersection of multiple lifetimes feature. So, when I do this lookup if it already exists, lookup, allocate, initialize, and then I want an add to objects. So the way this has to go is kind of a straightforward loop. We're going to visit all of the objects. And then for each of those objects, I just want to have a call that's like lifetime I have alloc object and stuff, right? Yeah, so what we're going to do is lifetime object add key, and then I take the object right here, I take the new key, and there we go. So now I just need to implement that and we'll be done. So I'm going to put this right here. Lifetime object, lifetime key, and I kind of want to pull this up over here and read it for a minute. So yeah, I see. So what we want to do is figure out what the last node is, which we can get right there. If the last node is 0, we'll go down this path, otherwise we go down this path. So the last node is 0, it means we don't have any key references yet. So we're going to get a new key reference node. New key reference node equals, and here I'm going to need the lifetime allocator. And that's going to come from the free key references dot first. If that is equal to 0, then we need to do an allocation. So we'll do this is equal to first again at the end, and zdll remove and then we need which means we need this. So on the general memory, we allocate a new node times the new node count. This doesn't need to be 256, it needs to be like 32. And then new key reference node, Right, so we grab the new nodes, and let me go over here to where I was getting the new object count. Yep, right down here. We're going to do basically this thingy right there. Except that we're dealing with lifetime key reference nodes. New node putter, new nodes, new node putter, I is less than new node count, ZDLL pushback lifetime allocator, free key references first, last, and new node putter. Then the new free key references count is going to plus by the new key count, new node count, and then we finally get the thing we needed to get in the first place, and then we pop it off of the free list. Okay, so there's getting a new key reference node. Now what happens? Well, we want to push it onto the object's list of key reference nodes. And then we want to initialize that. So let me go over here and look at the key reference node struct. What has it got? So next and previous have already been initialized. We're going to memset the new key reference nodes keys to 0, like that. And then we're going to set the first one to the new key. So ZDLL stands for zero-ended doubly linked list. I have a set of macros that do all my various linked list wrapping. So DLL underscore stands for doubly linked list, insert, remove, etc. ZDLL is the same as that, except the DLL version uses a sentinel-based list, and ZDLL stands for zero-ended, as in it doesn't point into it's not a continuous loop with a sentinel. It has 0 ends, where the next of the last thing and the previous of the first thing are both zeros, and then you have a first and last pointer to keep track of where they are that is separate. And then there's SLL for singly linked list. So I put that on right there, and then the objects, let's see, key count can go up by 1. So that's good. And then let's see. Cool. What do I do when I do have a last node? Well, the first thing I need to do is see if I have any room on it. So next insert slot equals the object's key count modulo the array count of the last node's keys. So if next insert slot does not equal 0, then all I have to do is take the last node's keys and set the next insert slot equal to the key pointer. Otherwise, okay, so otherwise, if it does want to put it at 0, the problem is that the last node is actually full. All 32 of its slots are taken. So now, I need a new node still, which means I want to pull out the thing that allocates one of those nodes, because I'm going to have it in 2 places in a second here. Lifetime alloc key reference node, general memory, lifetime allocator. And then this needs to happen. So we'll call this result, and we return it right there. And then this can just be set to lifetime alloc key reference node, general lifetime allocator. And then all of this is oh, whoops, that's the wrong spot for it. Right there. So new key reference node equals alloc key reference node, and then all of that is automatically handled. When I do that, if I rename this to new node, it will make the code better. There we go. So now I allocate a key reference node if I don't have a last node at all. I allocate it, and then I that should actually be up here. And then I insert it onto the objects linked list, and I clear its keys to 0 and set the first one to the key that we're trying to use. That's a pain in the butt. So, if we're in this code path, it means we did have a last node, but we needed to insert a new node anyway, so we get a new node, and then we literally do all of this again. Okay, so what that says to me is we want a insert on new node equals false, insert on new node equals true, insert on new node equals true. If we need to insert it on a new node, there's the job. So if we either don't have a last node at all, or we did have one but there was not room on it for the new key, then we allocate a new node, push it back, and we set the key right there. Alright, and now that it looks like that, maybe I'll leave this as a separate function just because it's, you know, the way things happened to end up, and it doesn't kill the code to be organized this way because the names get kind of long if I do it the other way. So, only problems are this now needs general memory. General. Lifetime key table erase is not even written yet. Still have to write that one. Okay. Pointer to right, so I need a lifetime key reference node pointer, and there's our names getting really long still. Lifetime key node, lifetime key ref node. lifetime key reference, lifetime key ref node. Table array, still gotta write that. Pointer dereference arrow. Oh, pointer dereference arrow again. Erase, and then let's see, what did you catch here as a warning? ZDLL removed, not enough actual parameters. Sorry, forgot the comma. What do you got next? Erase, free key. You're looking for the general memory. General. Key erase, general, general. Object add, key, needs the general, and the lifetime allocator. Erase, free object, needs the general, and again free object needs the general. Now we need to implement lifetime key table erase. So key table copy, insert, lookup. Here we go one more time. It's going to be a lot like lookup. Lifetime key table erase. So in this version, we're going to be taking in just a lifetime key. And when we get down to the point where we need to compare two things, the really cool part here is that we can just compare the pointers directly, because the only valid pointer, because the pointer, these are objects that are allocated in sort of unique ways, so two things are not identical for having the same memory, or rather the way I should put it is if they have unique memory, they are unique identities, and if they have unique identities, they are unique memory. Like, there's no such thing as having two different keys that exist with the same value in different places in memory in this system. So I can just compare these pointers directly to find out if they're equal. And if they are, I do this work here. If I find an empty spot, I just quit right then. And you know, it's not totally clear why I don't just do that, actually. It's what's going to happen anyway. Okay. So, if we find the match, then hashes index equals lifetime hash key hash slot lifetime, okay, what am I missing here? Lifetime key hash deleted, and the key slot gets set to 0. Alright. Build. We don't need set size. We don't know the hash, do we? That's right. So in this case, we actually have to compute the hash by going back. How do I compute the hash again? I go lifetime key hash erase key object or members erase key count. Not all control paths return a value because there's still the if on the outside. You're right. You're right. Okay. And okay. Alright, I will be back. Let's see, we're about an hour and 45 minutes. I want to do one more stream of this length after a 10-minute break. To debug all of this, because we've just finished implementing it, I need to actually put some of it to use in the custom layer somewhere and see it break and make it work. But before I do that, I need a quick breather, so be back in 10 minutes, 15 minutes-ish. See you in a bit.